In this video, I'll explain how the code works to do the Bayesian computation for the posterior of the parameter p in the dice simulation. And then at the end of the video, I'll explain how to use Laplace's approximation to compute the standard deviation or the covariance matrix of the posterior of the PDF. And we went through a little bit of it last time. So the first part is to just simulate a random sample. N is the size of the sample. Let's just make it small for this time. So it'll draw, in this case, 20 samples. So it drew samples, so data are the roles, and I got two sixes followed by 3 ones, 2, 1, 6, 1, 4, 1, 6, and so on. And I could sample again, so I just call data role p true n. And there's a sample, so the number p true could be anything between 0 and a quarter. So if I put in 0, I get only 6s, 1s. And if I put p equals 0.25, then I will get only 2, 3, 4, or 5, but no 6s and no 1s. Okay, so in this case, I simulated a biased dice with a pretty strong bias, where p true is 0.1/10 instead of 1/6, which would be for an unbiased dice. After that, I make a range of discrete values at which we're going to evaluate the posterior probability for the parameter p. So on a computer, everything has to be discretized. So what I do is I discretize the PDF in intervals of, or on the interval of 0 to 1/4 with 200 steps. So that number of steps could be changed. It could be made bigger or smaller. And then some of the subscript routines require p to be a column vector. So I convert it to a column like this. And then the first thing I do is I'll plot the prior. So here is the plot in figure 2. The x-axis is p and the y-axis is the prior. And you notice I do the exponential of the logarithm of the prior. And so my function that evaluates the prior evaluates not the prior itself, but its logarithm. Prior. Alright, so this is where the code is for the log prior. And it's very simple. It just takes the logarithm of the value of the prior, which is either 4 or 0. It's 4 if it's on the interval of 0 to 1/4, and it's 0 outside of that. So this is how it's done with these conditional statements. So if p is greater than or equal to 0, good. And if p is less than 0.25, good. These parentheses evaluate to 1 when the condition on the inside is true. So that's MATLAB syntax. So the first one will be a true statement if p is greater than 0. The second one only if p is less than or equal to 0.25. So, and then we multiply that all by 4 because the prior density is 4. Alright, so that was simple enough. And then so if I want to plot the prior, I need to re-exponentiate it. Okay, so this is the probability of p. It says conditioned on the data in the title because I'm going to make the same plot later on, but it's really just the prior. Maybe I could change this title for the first time. Alright, so this over here is the plot of the prior. After 0 rolls, the true value of p is put in the title so we can see if it's working. And we'll hit return. Okay, so now there is one sample draw. So I have this little program that will draw the face dice. So let's look at that. That's not really that important. So the first thing, the way the code works is after drawing the full sample, first time through the loop I'll consider the first sample only. The second time I'll consider the first 2, then the first 3, and then the first 4. So I'm not really using the Bayesian property that you can use it to update from the previous calculation, the new one, by considering only one additional bit of information. I consider either no data, the first data point, or the first 2, or the first 3, and each calculation is done independently. So it wouldn't be very difficult to modify the code to, once we've already computed the posterior for samples 1 through k, then do samples 1 through k plus 1 by simply using the prior, by using the posterior when we had k samples as the prior for when we have k plus 1 samples. That wouldn't be very difficult, but it's not the way the code works now. We can maybe modify it later. Okay, so the first time through the loop, the first thing we do, or every time through the loop, we plot First, the posterior. So I have this command here, post equals posterior, and posterior is a function that I wrote, we'll look at in a bit, and it takes two things. First, the range of parameters p, the discrete set of vector, at which I'm going to evaluate the posterior, and then the data set to be considered. All right, and then it's going to make the plot. Oh, I forgot to point out. So the first thing, it makes this little face plot. So this is the plot that made this little dice face. So that's not so interesting. It's just plotting circles. There's just a switch, and if the dice is 1, then it goes off and it plots 1 circle in the middle, and if it's 2, it plots 2 diagonally, and if it's 3, it plots 3, 4, and then 5, the usual faces. So, and it just makes the marker size very big so that they look easier to see, so that they're easier to see. Okay, so let's look at the function posterior. So everything follows from there. All right, so here's the function posterior. So let's start how the calling sequence work. So at the top we have posterior. And posterior, the first thing it does is calls a function called log posterior. So everything is being computed using the logarithms of the probability distributions. And that's important because when we get to very big data sets, the PDF itself can become very, very small, and it becomes hard to compute if you're working with the actual function itself instead of its logarithm. So everything is done in log space, and we check for underflows along the way, and I'll show you where that happens. Okay, so let's assume that log posterior works. So we have the logarithm of the posterior PDF as an input, and then the first thing we do is we're going to subtract the maximum of log p from the logarithm of the posterior, and that is precisely to avoid underflow. So, you know, if you have a really, really big data set, the likelihood function, sorry, not the log likelihood, the likelihood, right, is going to be extremely small because it's going to be considering the probability for having a particular sample of rolls of a dice. So let's say I've rolled 1,000 rolls, and so I have 1,000 number, so the value of the likelihood is going to be on the order of p raised to the power of 1,000, and p is a number of order 1/10, and so 1/10 raised to the power of 1,000 is 1 over 10 to the 1,000. It's going to be like of order to the minus 10,000, so which is an absurdly small number, right? And so because that would just lead to an overflow and you just get a 0, the first thing I do with the logarithm is I subtract the maximum value of that logarithm. So now I'll have a bunch of numbers where the maximum is at 1, and the other values of the log posterior are going to be decreasing from there. And then we can re-exponentiate that after having subtracting. So now I know that at least the maximum is 0, and when I do the exponential of 0, I'll have 1. So the y value here is going to have its maximum at a reasonable number of 1, and the other values nearby will fall off and eventually go to 0 out in the tails where the values of p are not very probable. So this log posterior is not normalized yet. So remember when we did Bayes' theorem, we have the probability, oh, we can't see down here. We have probability of p conditioned on the data and the prior information is just proportional to the probability this here, there's missing the normalization constant, so I have to make sure that the integral of this thing sums to 1 or integrates to 1, and that's the next thing that's done. After rescaling and re-exponentiating, I'm going to do the integral of y with respect to p using this routine called myTrapZ, which is a function that it implements the trapezoid rule. And so it does almost the same thing as MATLAB's built-in TrapZ function. I just wanted to have one written in here so that you can see how it works. It just does the trapezoid rule of integration. So after, at this stage y, I have a discrete value of the posterior PDF, unnormalized, bunch of y values. And then I'm just going to do the integral under the curve and divide by that to make sure that now it integrates to 1. And then I plot y divided by z, so the normalized posterior. And after one roll, it produced this graph here, this triangular shaped posterior PDF, starting at a maximum at 0 and then going all the way down to 0.25 at 0 at that point. And right, like I explained last time, p cannot be 1/4 because then 6 would have 0 probability, but we got a 6. So the Bayes theorem figured out right away that p cannot be 0.25 with one rule, even though the prior was flat. Okay, so then we should go back now and look at what log posterior does. So it's easy, it's just up here. So log posterior computes the logarithm of the posterior. So it just takes the log of this expression down here. Oh, we can't see again. It takes the log of this expression over here. And so it takes the log of the prior. So this one calls log prior. And it also calls log likelihood. So log prior is this one. It's the log of, of this one. And log likelihood is the log of this one. So log prior, we've already looked at it. So that's fine. It's just a constant, so it doesn't really add anything. Since it's an unnormalized, I could have skipped this stage, but later on maybe we can try the code with different priors to see how things work. Okay, so log likelihood, that one is just a little bit above here. And it takes in the data and the range of parameter, the range of parameter values that I want to evaluate. And so log likelihood is going to evaluate, just like log prior did, the logarithm of the likelihood function for each value of p. So here it's going to compute this thing. If I discretize p with 200 points, then it'll evaluate 200 values of the log of the data, the log of the probability of the data condition on the p. So all 200 values. So the code is vectorized. So then for each value of p, it computes q, and then it makes a little vector of probabilities, q, p, 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 and q. So those are the probabilities. The first one is for the probability of 1, which is q, the probability of 2, which is p, probability of 3, which is p, 4, which is p, 5, which is p, and 6, which is q. And then, provided that the data set is not of 0 length, it will take the log of the probabilities, so this probabilities of the data, and then sum the second column. So how does that work? So these are the probabilities. So the data are discrete numbers, 1 through 6. So I use the data as the indices into this probability function. So remember, the data set has discrete values. It could be 1, 2, 3, 4, 5, 6. If I rolled a 2, for example, then probability of 2 is going to pick out the second number inside this probability distribution, so it'll pick out this value, which is p. If the first data is 6, then it'll pick out the last value, which is q. Right, and then we do the log, we sum the log of all those evaluations, and we call that L, right? Because the likelihood function, this one, probability of the data, and suppose that the data, to be concrete here, suppose we had this following data set. Probability of getting that particular data set. So the probability of 2 is p, the probability of 1 is q, the probability of 6 is q, the probability of 2 is p, and the probability of 4 is also p. So this would be the likelihood function for this particular data set. And now if I take the log of the likelihood, then this will become and then so on for the length. So this is all this does. It just sums those logarithms and assigns it to the value L. And then this gets passed to log posterior, adds on to the log likelihood, feeds it back into posterior, posterior normalizes and plots it. And that's all there is to this code. I can show you what the other subroutine. So we've looked at roll already. This is the loop, log prior, log likelihood, log posterior, the posterior, and this is a little trapezoid rule integration. It just computes, you pass in the x and the y, and it computes dx, computes the height using the trapezoid by taking the average of the two edges, and sums all the areas and returns the values. And then down here I have a little program that plots the face values. So it's easy peasy, super simple. Let's keep running it a little bit. All right, so that's how it works. I wanted to point out how we can do estimate the mean and the variance of the posterior PDF using something called Laplace's approximation. And so I'm going to explain how this works. And so the idea is quite simple, is to simply expand the logarithm of the posterior PDF in a Taylor series and then truncate to second order. And the point at which we do the expansion is about the maximum. So if this is the posterior, so suppose that this is the probability, so this is my posterior, and I take the log of this, and I'll define this to be L. So that's the log posterior. And I'm going to expand the log posterior in a Taylor series. So what I have is L of P is equal to L of P. I'll put a little hat here. So that's the point at which I'm expanding the Taylor series. And this P hat, we're going to pick it to be the maximum. So I'm going to take the maximum of the posterior. I'm going to find the maximum. And at the maximum, I'm going to expand in the Taylor series. So we have this plus dl dp. I don't really need a partial derivative because L in this case is thought of as a function only of p. So I could have written this the regular derivative. And this again is evaluated at p equals p hat multiplied times p minus p hat plus 1/2 dl. So now the second derivative, dp squared, evaluated at p equals p hat times p minus p hat. And then there should be higher order terms, and we're going to truncate. So neglect higher order terms. And now if I chose my p hat to do the expansion to be the maximum of this function, then dl dp is going to be 0, right? At a maximum, the derivative goes to 0, you're increasing, and then the slope goes to 0 at the maximum. So this term is equal to 0 because p hat is the maximum of L. And so I can neglect this term. And all I'm left with is these two terms. So I have L of p hat plus 1/2 d2L dp squared divided by p equals p hat multiplied by p minus, oh, I forgot here, there's a squared here, right? The Taylor series, p minus p hat squared, that's important. Squared, like that. So this is my approximation, and then since this is the log of the posterior, to get the actual posterior, I'm going to re-exponentiate this. That will be inside L p hat, that's fine. All right, so then that means that probability p, condition on the data, is going to be approximately equal to the exponential function of L of p hat plus 1/2 L primed evaluated at, L double prime, sorry, the second derivative, evaluated at p hat multiplied by p minus p hat squared, close the parenthesis. And this can be further simplified. Minus 1/2 sigma, and I'll explain what sigma is, times p minus p hat squared. Where sigma is going to be where sigma is equal to 1/L double prime of p hat the minus sign, right? Because I have the minus here. And the reason I wrote it like this is that this now looks just like a Gaussian, right? Like a normal distribution. So this is a Gaussian, or normal distribution. And so we can get the standard deviation. Oh, there should be a squared here. Sorry. I want a square to make it a Gaussian, and I want a square down here. Like that. No, no square here. No. Sigma squared is this. Ah, I'm messing up here. Yeah. L double primed minus L double prime reciprocal is sigma squared. And then this is sigma squared. So the standard deviation sigma is going to be equal to the square root of minus 1 over L double prime evaluated at p hat, which is at the maximum. And L double primed is always going to be negative, right? Because if we're at a maximum, if p hat's a maximum, then the log posterior is going to look something like this. Remember, sad face for negatives, right? So this will be negative. The curvature, the slope is first positive on this side, and the slope is negative on this side. So that means the slope goes from positive to negative, so it's decreasing. The derivative of the slope, I mean, is decreasing. That means the second derivative is negative. And so negative, negative makes it positive, so it's perfectly fine to take the square root to get sigma. And that's how we can get an error bar using this Laplace approximation. Now for the particular case of rolling the dice, that is easy this time. Suppose we roll the dice and we have a data set. All we need to do is count the total number of times we got the numbers 2, 3, 4, or 5. So suppose that's n is my sample size, and then little n is the number 2, 3, 4, and 5s. And then n minus little n is going to be the number of 1s and 6s. And so then the log, or then the likelihood function, which is going to be p, so the likelihood is going to be proportional or equal to p to the power of n times q to the power of n minus n. And remember, I can rewrite q in terms of p, so this will be p to the power n, and q was equal to, I can never remember, so I have 0.5 minus 2p to the power of n minus n. And now the posterior, the log posterior is going to be the log of this plus the log of the prior. And the log of the prior is a constant, so we can neglect it in this case. And so what I have for L, the log posterior, is going to be equal to n times the log of p plus n minus little n times the log of 0.5 minus 2p. And then it's easy now to take the derivatives. So L primed is equal to n over p plus n minus n divided by 0.5 minus 2p times minus 2. And then I can now evaluate, set this equal to 0 to find p hat, and then I differentiate a second time to get L double prime. So you can kind of see how to do it. I'm not going to do the algebra now. I'll leave it for an exercise for you guys. All right, so that's the end of this lecture.